Welcome back. In this video, we'll be discussing anti-dihydroxylation. So we're adding OH and OH across a double bond in anti-stereochemistry. So in this case, you see that we have ethene or ethylene here, which is the common name for it. And if we do a dihydroxylation reaction, we're going to add OH and OH to alternate sides of the double bond. So in this case, we produce ethylene glycol, which is used as an antifreeze. So anti-dihydroxylation is a two-step reaction process where in the first step we take our alkene and we use a peroxy acid, this RCO3H, to produce an epoxide. And that's step one. Then in the second step we use acid in the presence of water to produce the hydronium ion that's going to open that three-membered ring of the epoxide and produce a trans diol. So this is an alcohol where the OH groups are on adjacent carbons. So this first reaction, the RCO3H, producing an epoxide, we're going to see a lot as we move through the course. It's a reaction in its own right and it has merit because epoxides are used to produce resins that you might have heard of, like epoxy glues or resins maybe for your floor covering. So it is a two-step process. In the first step we produce an epoxide, in the second step we open that three-membered ring to get a trans diol. So in the first step, again, we have a peroxy acid here. So it's like a carboxylic acid, but we've got this extra oxygen, and that's why it's called a peroxy acid. And so so we can have different R groups here. We're going to look at a couple of different ones. We have peroxyacetic acid here, metachloroperoxybenzoic acid here, MCPBA. These are going to be the most common ones that we're going to see. So for this reaction in the first step, the alkene is going to, and this seems a little odd, attack the oxygen of the peroxy acid, forming this bridge transition state, okay, which collapses to give us an epoxide. And we're not going to worry too much about how this whole thing happens, but we get an epoxide and then the acid as products, okay? So here are the peroxy acids used in this reaction. So the most important thing is to know that we get this epoxide as a preliminary product in our reaction. And to open that epoxide, we can open that epoxide and get the trans diol. To do that, we use, in this case, we're going to use hydronium, which is acid in the presence of water. The epoxide is protonated in the first step. And we form this three-membered ring with a positive charge. This is starting to look a little bit familiar here. Now that makes that three-membered ring have a partial positive all the way across it. So the carbons are going to be susceptible to nucleophilic attack. So water functions as a nucleophile to attack the three-membered ring and open the ring. That's why we get anti-addition of these oxygens. So we have this positively charged intermediate that can be deprotonated to give us our product, okay, which is the trans diol. So remember, like I mentioned earlier, that three-membered ring, the protonated epoxide, is very similar to the bromonium ion we saw earlier and the mercurinium ion we saw earlier. So that positive charge on the three-membered ring is shared across the entire three-membered ring. So we have a partial positive on the carbons as well, okay? And so for the bromonium ion, same thing. That's going to make those carbons subject to nucleophilic attack, okay? And so all of these reactions yield anti-products because the nucleophile has to add from the opposite side because it can't add from the top because it's blocked by that bridging ion, okay? So let's see if we can predict the major products of these reactions. So we have our RCO3H, which is peroxyacetic acid in this case, okay, and then H3O+. So what are we adding and where are we adding it? And how are we adding it? We're adding OH and OH across a double bond. We're going to add those anti, okay? so for this particular substrate, we're going to add, let's say the methyl group is going back, then the OH is coming out, the other OH will be going back, plus the enantiomer. For the second one, we've got, let's say, an OH going back, then the other OH will be coming out, but it doesn't matter because that's not a chiral center, so we can just draw it like this. But that is a chiral center on the left, so we can say plus En. Why is it a chiral center? Because we've got hydrogen, OH, propyl, and this CH2OH group. Alright, let's see if we can predict the products of this reaction are CO3H or some peroxy acid, followed by aqueous acid. So for A, we've got what? It's a really bad drawing, isn't it? Alright, so what are we adding and where are we adding it? We're adding OH and OH anti to each other. Okay? So if we've got one of the methyls on a wedge, the OH will be on a dash, the other OH will have to be on a wedge, and this methyl will be on a dash, right? So for the, and then plus En. So for B, we've got OH and OH, and that's plus En because that's not the meso form. Okay. And for C, we've got OH and OH, but if we rotate about this, that's going to give us, it's still not meso though, so, right? Okay, we could have gotten that. That would give us that, but then let's think about if we had the enantiomer. This OH is on a wedge, this OH is on a dash, and we rotate, and that's going to give us this thing. Okay, so those are enantiomers of each other. Just thought I'd explore that a little bit. So for D, we've got, we're adding here, and we're adding, say here, the chiral center is on the left, so we can say plus En. Alright, and that's anti-dihydroxylation. I'll see you in the next video.